Our next speaker is Angie Stacy. She's a professor of chemistry at the University of California, Berkeley, and she's a material chemist, and she studies solid state, physical, and inorganic chemistry, but she also does a lot of work on education and diversity issues. She has a BA from LaSalle College and a PhD from Cornell University. Her postdoc was at Northwestern University. She's won numerous awards for both her research and her education, and these include awards such as a National Science Foundation Presidential Young Investigator Award, the Distinguished Teaching Award from the University of California, and the Don Sterling Noyce Prize for Excellence in Undergraduate Teaching. She'll be talking about assessment, and she's been working with John Hutchinson on the committee to revise the new Advanced Placement Chemistry test. So she's an expert in this field, and we welcome her to us.
Thank you very much. So it's a real pleasure to be here, and at the outset I want to say that I've really resonated with all of the talks that we've heard, and I hope that I will be able to add to the discussion by considering how we really do determine the content knowledge that we think our students are walking out of our classrooms with. And just by way of a little bit of introduction to myself, I started in the mid-90s when NSF had these major grants that they were giving out for chemistry initiatives. And at that time, we thought with the size of the grant that they were giving us that we would be able to reinvent the entire undergraduate curriculum. Instead, we realized that we had to focus on the general chemistry curriculum, and at the time, we were really looking very far away from where we were to pretty much a context-based course. And what we rapidly realized is that the majority of the faculty are over here, and we're thinking way over here, and they're not ready to move that far. So we really feel that we needed a lot more work to make our materials good, but at the same time, we were leaving a lot of people behind. I then moved into high school chemistry because I felt that I could really study the high school classroom better because of its size. And for 10 years, basically, we worked on a curriculum that's now published, but it's called Living by Chemistry, that is very similar to many of the things that you heard here, that supports the high school teacher in having an activity for every day of the week. Could be an experiment, could be cards, could be worksheets, just lots of different ideas to help the students learn. Now, I'm back to Berkeley and the undergraduate course, and that's what I want to tell you about today. And the work that we've been doing with this very, very large environment that we're in, 1,300 students in the class, divided nicely into 3 lecture sections, and many lab sections. So this is similar to some of the things that you've heard today. So my collaborators are Michelle Dusky, who is a lecturer, phenomenal mentor of the teaching assistants and co-conspirator, and then 3 graduate students, Paul, Tatiana, and Michelle. And then I want to acknowledge Kathy Scalise, who got her PhD degree with Mark Wilson, who some of you may know, doing assessment in the School of Education. And we continue to collaborate with her on the statistical analysis of the assessment data. Okay? All right, so I'm going to get right to the study that we've done. And what I want to try to persuade you of is that very second line up there. What gets measured is what gets learned. And that's something that we haven't talked about yet in the talks that we've heard. How do we hold the students accountable for the learning that we want them to do? So the expected project outcomes, here's kind of the hypothesis, is that we could create test items, and I call them near transfer test items, that you cannot answer if you simply memorize the algorithms. Now, our students come in, we've selected out those who are very, very accomplished at memorizing algorithms, and what we wanted to design were problems that they could do. And my criteria is that when they see the answer, they go, oh, I should have known that. All right, but they couldn't memorize it. And so we're really looking for them to apply the normative chemistry models. Now, the data and methodology to assess our progress in this is threefold, and that's what I'm going to tell you about. Is first of all, how we use item response theory which is a statistical method for determining whether your test items are actually doing what you think they're doing, rather than just sitting down the day before and writing some random questions and hoping that they might measure something about the students. We've been doing a lot more analysis of the test items. We also have student surveys that we collected multiple times, multiple semesters and 3 times during the semester. And as you'll see, we interviewed a lot of students to validate what we were learning. And our major findings I'll put out there right now so that you can see what evidence we have for these findings, is that students who are given more practice with the kinds of questions that we wanted them to be able to do, they perform better on the assessments that require deeper understanding. You may not be surprised by that. We tend to give them algorithmic problems, and then on the test we give them all these clever problems. Well, if they haven't had experience with these clever problems, they're not going to do very well on them. And we have definitely found that our students will change their strategies based on the test item type. And I want to show you the evidence for that. Okay, so here's UC Berkeley. It's 1,350 students. One thing I'll say about our students is, first of all, they are majority California right now, although that's changing. And about 1/3 of them are on Pell Grants. Many of them are first in their family to go to college. So while we have a very motivated group and top quality, they really do have a range of backgrounds. And let me remind you, lest you think this doesn't apply to all the schools in the Houston area, these students come from high schools that rank 49th, okay? We're better than Mississippi, all right? So just keep that in mind. I don't want you to think that these are great students, they're highly motivated, but they really do have a range of backgrounds. And you see that we are largely have an Asian population, but that population ranges from 4th generation Chinese to new immigrant with ESL or language, you know, where they're learning English as a second language. We have many who've taken the AP chemistry test, but that really varies what that means. About 28% of them express concerns that they might not do well in this course. And so you see kind of the demographic. And we are 60% female. So that's pretty amazing. And the faculty teach collaboratively, at least for the course that I teach. I have 3, 4 other faculty who we work together, and we really jointly try to decide what's the best approach. And we critique each other. They actually critique me because I teach the first lecture, and then they sit there, and then right after it they go, you should have done this and you should have done that. But it's been wonderful because we've really had the opportunity to improve what we're doing. We frame the course around the big ideas in chemistry. So this is immediately tying into assessments. What do you want them to get out of the course? And in a nutshell, I want them walking out of the course, looking around at the world, and they're imagining what the atoms and molecules are doing and explaining things based on that. Why? Because it's a very useful model in terms of understanding what's going on. They laugh at me, but in fact they start talking about the molecules moving faster today than yesterday because, of course, the temperature's higher. But we are really framing it around matter. Again, it's this atomic view linked to the real world. What are the atoms and molecules doing? Change, how is that happening? What is happening when you see something that looks one way and it now looks another way? What has happened? And we talk about how atoms, ions, molecules rearrange. We talk about energy as important in being associated with this change. The 4th area is light, where we use it as broadening our vision, that we can use light and instrumentations designed based on the interaction of light with matter to actually learn a lot about matter. And then more recently, we've added green, meaning that we have worked in the laboratory to not just get the students to think chemistry is about maximizing yield. That's what the calculations have been for 50, 60, 70 years. But instead, it's not just about yield. It's about where did the chemicals come from and where are they going to end up when you're done. So to really teach the students this bigger idea of how science interacts with the environment. We use a course that's designed on the research literature. I put it in terms of the 5E model. There are many similar learning cycle models. The main thing that I want to point out is that we start our class by engage. And what we do for that is a pre-class assignment that anybody in the room could do, whether you or not you are familiar with chemistry, whether or not you're taking a chemistry course. Because it's about observations, it's about data, and it's about patterns. Just what do you see? And that pre-class assignment is the focus then. It's the observations, it's the data around which the classroom interaction is structured. We also use demonstrations. Every lecture has several major demonstrations that are done very carefully with hypotheses and observations, and then a discussion of how we can understand what went on. So the explain part, we do some lecturing, but that comes after they've had some experience with the data and they know what the goals are and what we're trying to do. We have an elaborate portion where we have study groups that where the students can really start to think about the material with one another. We have discussion sections that are very student-centered, online homework, office hours, and then most recently we've gone to study guides. And what I mean by that is I didn't assign a textbook, which shocked many of them, and instead I asked them to go out to particular websites. I gave them words that they could look up, and I asked them questions to help them kind of generate their understanding from the information that's out there rather than this linear reading of a textbook. In fact, our study showed that those who were reading the textbook and outlining it were spending an enormous amount of time, and they were not doing well in the course. That was clearly the low end. I can tell you what they were doing, reading the textbook and outlining. And that doesn't mean I think reading isn't good. It's that they weren't comprehending, they weren't reading with a purpose, they were simply transferring or highlighting. And then we use a lot of iClicker questions to evaluate, to help the students evaluate where they are. And then mostly I want to talk about the exams, which really changed behavior. All right, so let me say something about norm-referenced assessment, which is what we all do. We write a test. We have no calibration of anything. And then what we do is we curve it, and we compare people relative to one another. So I've got Julie with an 87%. So I don't know whether she's just as good as Joe. I don't know whether they're both absolutely excellent or they both know very, very little, because I have no calibration on this. And so what we set out to do, which was not trivial, was, and we're continuing to work on, is to ask the question, where would Julie fit if we had levels of thinking in chemistry from the novice who comes in knowing very little all the way up to what we might call the expert. And so what we'd really like to track through all the courses and all the years of study is where does this student really fit. So we use item response theory, which I'm not going to go over in detail. It is a statistical method that allows you to look at each question, called items usually, each question, and estimate the difficulty of that question. So you might have written a question, could be open-ended and have different levels of difficulty, could be a multiple choice that has a single level of difficulty, but you want to know how does each question compare to all the other questions statistically? Are they of comparable difficulty, or some more difficult, or some less difficulty? And at the same time, you want to know about the student performance estimate. So you want to assess the odds of getting a certain average score. Now, let me just explain what I mean by all of this. Right now, very few of you know for an individual question whether it was random who got it right, whether it was the top students who got it right, whether there was some confusion in that question and it was random who got it right. And so what we're trying to decide is if this is all working well and we know the difficulties of the questions, then the majority of the students should come to some level where they get all of these right and all of these wrong. All right, that's what we're looking for. And so we want to know what level each of these students gets to, and that's what this will do for you. And I love the thermometer analogy because it brings it back to science. All right? I would like to know, back in California, what's the weather? Well, I don't say it's warmer or colder because you don't know what that means relative to Houston. We have a thermometer that's calibrated, and you know how it's calibrated, so that I can take it anywhere in the world and I can measure the temperature. And I can tell you what the temperature is, and I know what that means. And so that's what we're trying to achieve with assessments. All right, so we've been using different levels of success that are very much like the taxonomies that you've seen. This particular one that I'm showing you, let's start with the ABC. So here's what I'm imagining. The D student never uses chemistry. The D student, we find actually our high school students have great logical reasoning, but they don't use a lot of chemistry in that. The C student should be able to recognize things, which is mostly what sometimes we assess almost exclusively. And what do I mean by recognize? That you can make this link to that, that if you've seen this before, you can do it again, or you know what this word means and what its definition is. So it's a very simple connection. And we are calling that C level, and we let the students know that that's C level. They are beginning to use chemistry ideas. On the open-ended questions, they may use those ideas incorrectly. It's okay. They're using chemistry. They're starting to speak the language. The B level, we call formulation. And what students are starting to do is understand some of the formulas. And I don't mean just mathematical formulas. I mean models. They're making some more than just one link. They're starting to understand how to use the ideas to explain things. But that's our B level. Our A level is when the students can deal with ambiguity in the data. They understand the limitations of the models. They show scientific thinking truly beyond memorization. And as many of you know, students can learn something in one context, and we see this all the time in math, that our students are doing calculus or beyond, yet they can't answer simple algebra questions. That doesn't mean that they weren't taught well in algebra. It means that they didn't learn it at the level to be able to transfer it to this new context of PV equals nRT. I mean, that's a great example. Plot P versus T, what's the slope of the line? And my students just look at me like, what are you talking about? And they're quick on the uptake because they've already learned a lot of math, but it's that connection that they're not really making. And this is just a sample question. I don't want to go into the details of it, but when we do open-ended questions, I have my teaching assistants score the question in the following way. To be consistent with how we design these exams, we don't have random numbers of points. The points for each question are kind of similar. So if this were a question that went all the way up to the A level, to the connections level, what I would expect is a complete answer, an answer that's partially correct, an answer that kind of addresses a little bit of the problem, and then it's just pure nonsense. And at first, the graduate students were very uncomfortable with this because they'd say, well, this one's just a little bit better than this one, and they'd want to give it extra little quarter of a point or something. I said, no. If we ask enough of these questions, on average, we're going to get it, whether the students are at the C, B, or A level. So on the first exam, where do you think they all were? They were all B, but they roughly B level, some of them at Berkeley, okay? Now that was really interesting because the TAs were very upset. They said there's no spread. I said, maybe there isn't. And in fact, that's what we concluded. There really isn't a spread at the beginning. And once the students understood the level that they needed to get an A, they started to really change their behavior and the responses they would give. All right, now here's an interesting study that we did. We used a discontinuity design, which means that we treated half of the class one way for the first part of the semester, and we treated the other half of the students a different way at the second. We switched them midway. This was for human subjects reasons. So we randomized them into 4 subgroups. All right, now, the O simply means when we observed them. We observed them pre, mid, and post. That's all the O means. Now, what's important is the X. So the X indicates the treatment assigned, the educational intervention. So what we did was we gave 2 groups of students conceptual questions on the homework. We swapped out the standard homework questions with ones that were closer to the behaviors that we wanted. They were actually multiple choice, but they still caused the students to think much more deeply. And then the other students got the standard homework questions. And then at the middle, we swapped. All right, that's what this is trying to indicate. Now, there was one other thing that we did. With the 2 treatment groups, one of them just got the questions. One of them got the questions plus feedback. We let them know how well they were doing and what they needed to do better. All right, questions on that? Okay. All right, so we call the assessment system ChemQuery. The level of achievement, the 1 plus, and the 1 minus, that's basically down in the, that's the lowest level. They're using logical reasoning. The 2 minus, 2 plus is the next level up, this formulation level. And I heard some of you were kind of guessing this, this level. A lot of students are just at that level. And then this scale moves on up through to 5 or so. I think the main thing I want to show you here is that if you look pre, mid, and post, there is some gain. I would hope so. But what might be surprising is they really, depending on the items you use, are not moving that far that fast. Okay? And so that's been something that's been really interesting to us. It gives you a different view of the learning trajectory, because I think we're teaching up at the 3-4 level, by the way, and the students, when you're truly asking for understanding, are down more at the 2 level. All right, so this is just to show you that there's improvement over the course, but here's what's interesting with the treatment and comparison groups. Those who had the treatment at the start of the semester, the conceptual questions at the start of the semester, they did better even when we took those conceptual questions away from them. Those who started without the conceptual questions at the beginning of the semester, they did not do as well at the end, even though at the beginning of the semester these 2 groups were the same. So it's very important to send this tells us that it's very important to send the signal right away to the students as to what you're expecting on those assessments. And if your assessments aren't mirroring what they're doing in the classroom, they're going to quickly discount those and do what they think they need to do to get things right. In this case, on the homework, it was more algorithmic problems that wasn't really telling them what we wanted them to get out of this. So the findings then are that we have statistically significant improvement for both the original conceptual conditions, and they did better even after we took away the support that we were giving them. And then what was even more interesting is that for the group that had the concept questions originally, 43% fewer students who were identified at risk were in that group. So the at-risk students did a whole lot better if they had these different homework problems at the beginning of the semester. It turns out that the feedback that we gave, the differentiated feedback that signaled to the student what they needed to do, didn't lead to a significant difference. That doesn't mean that feedback wouldn't be a good thing. Whatever we were doing wasn't making any difference for the students. Okay, so now we went on to look at their, we call it student circumstances. So we did surveys of the students, pre, mid, and post, and have done a lot of factor analysis. These surveys, the one that we've worked on through a couple of years, factors extremely well and gives us, we think, pretty good information about the students. And so here's what we wanted to look at. We wanted to look at their beliefs about their own academic abilities, the support structures that we were getting, because my hypothesis was that if you came from a disadvantaged family, that maybe you weren't getting the support you needed, whereas if you came from, or you were my kid, you could call me and say, I can't do this chemistry problem, how do you work it out? So we thought maybe support structures were important. Family encouragement and pressure, we wanted to understand. Perceptions of the classroom environment. How do you feel as a student sitting in this enormous classroom and then being divided up into these smaller lab sections? And then, of course, we wanted to correlate with the demographics, the student demographics, and including what prior chemistry courses they had taken. Now, I'm not going to go through all the details here, but you see beliefs about learning science. And what we wanted to ask was, what was your belief about learning science, and how did that affect your use of resources? We found out that we didn't get very reliable data on that, so we weren't seeing any kind of correlation. We looked at perceptions of the classroom environment, and in fact, there is a positive correlation with your achievement, depending on how you felt about the classroom. This is related to Claude Steele's work, if you're familiar with it, stereotype threat. Are you feeling threatened in this classroom and that you don't think you really belong or that you're going to do well? We looked at external support structures, as I said, and what's fascinating is it's a negative correlation with achievement. Shocked me. And so I think what that means is that the students who, my hypothesis is that the students who have a lot of family support have basically helicopter parents who are saying, oh, it's okay, if you didn't do well in chemistry, you can go on and do something else. Whereas the students who have fought their way to the university actually were achieving better relative to that support structure. Now, here's the biggie, and that's your belief about academic abilities. If the student came in at the beginning of the semester and didn't think they were going to do very well, they didn't think they were going to do very well at the middle, and they didn't think they were going to do very well at the end. So there's a way in which the students have labeled themselves that over the course of the semester, we were not able to circumvent. And then this use of resources, we probed further in interviews with the students. Now, what I'm thinking about of use of resources is to do well in this course, we have preliminary findings that would say that if you just did one thing, I don't care what that one thing was, but if you just did one thing, you're not going to do very well. You actually need to use multiple resources. What do I mean by that? You go to study groups, or you look at the webcasts and take notes. You write problems for your classmates and you share them. You read the book, you look up resources on the web. So if you weren't accessing different resources, just doing one, and the worst one, like I said, is to simply, oh, well, I did all the problems and then I went over them again, as opposed to doing new ones and realizing that your classmates were doing many more problems than you were doing. So in the interviews, we could really assess what the students were doing. So we did semi-structured interviews, where we really focused on beliefs about learning science, students' use of resources, and if they changed their study strategies, what were the reasons for changing them? And we were trying to validate the student experience measures from surveys. And so we interviewed 78 students. And for those of you who do educational research, this was a heroic effort from 2 graduate students who did this 3 times during the semester. Now, the amazing thing is that the students came back and that they actually were happy to have us interview them 3 times during the semester. One of the slight problems is that observers make a difference. So the students would come in and we would ask them questions, and the interviewer was trying to be very neutral, and the students would leave saying, "Thank you, that was very helpful." And the interviewer was going, "No, no, no. I wasn't trying to change anything that was happening. I'm just trying to be a neutral observer." But it caused us to realize that focusing the students and asking them questions about what they were doing actually can help in terms of the choices they make. Now, I should say that these interviews were done right after a midterm, or an exam. So it really focused the students on, we would ask them, how did you prepare for that midterm? How did you do? How did you feel taking it? We could really learn a lot about the midterm exam itself. And the preliminary interview findings are as follows. Students who improved would report right at the beginning that they studied the weekend before. They thought they had everything memorized. For the second midterm, they studied a whole week before. For the third midterm, they were studying every day. All right, not more, just more consistently. And they learned that if they had not, since we built through the semester, they could not afford to wait a week or two to look at what we were doing, because we were building on it in each lecture. So they moved away from just reading the book. They started to work with peers, and they began to ask a lot more questions. The students who did not improve stayed passive. They stayed focused on reading the text, and they were not very reflective when studying. And the students made changes to studying primarily after the first or second exam. So the first one caught the people who hadn't had a lot of chemistry, and they already changed their behavior. Those who coasted through the first exam because they had had a lot of chemistry woke up big time after the second exam. And because they really slipped on the second exam and then came up once they realized what they needed to do. And I think the key here is that we've been developing questions that required application of ideas to new problems, and that they just couldn't memorize. They'd never seen it before. And the key to that, and I'll end with this thought, is, so what do those questions look like? Well, if you think of all that you've heard in the last today and yesterday, they start with observations. So these are all questions that start with data. Why does my blood look green when I'm at the bottom of the ocean? Or here's a table of data. How do you understand the trends in that data? And so if you start with observations and data, you can write many, 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 many new questions very easily, as opposed to simply asking the standard algorithmic questions. So this is where we are, and we're hoping to continue to push assessment ideas as a way of really fostering changes in both what we do, in what educational interventions we promote, and also what the student behaviors are. And I'll end there and see if there are any questions. Go ahead.
Asking conceptual questions up front, did it increase the number of students who dropped the class? Did they give negative feedback based on those conceptual questions and decide not to continue?
Not that we've seen. So they do. So the question is, does asking those conceptual questions get the students to drop? We're working very hard to. What we find is when the students understand something and can explain something, they think that's really cool. And so as long as we've encouraged them to say, and we say we think everyone in this classroom can do it, it's about putting the time and effort into it, and so no, we don't get a lot of people dropping. But we've had to learn to meet them. The jargon is the zone of proximal development. If it's too easy, they will trivialize it, they won't work hard. If it's too hard, they'll just get frustrated. So the other thing we are learning is how to adjust so that we meet them where they are. And then they get excited when they can explain things.
Thank you very much.
This program is protected by a copyright and may not be redistributed in whole or in part without the express written consent of Rice Digital Media Services.